So this is our last section on logarithms. So we're going to take one last look at some important properties of logarithms. We want to be able to solve equations with them. Our goal is always to be able to solve equations. Then we're going to look at applications of compound interest, and we're going to look at applications of base E for exponential growth and decay. So one of the properties of solving for our logarithms is, if I say x is y, then if I take and I raise x and y as an exponent on both sides with the same base, that's keeping the equation balanced. At the same time, if b to the x equals b to the y, my exponents have to be equal. So 2 squared is only actually equal to 2 squared. So that's what that property is saying. This is restating it as a logarithm. So log base b of x equals log base b of y if x and y are the same value. So log 2 has to equal log 2. And then number 4 is the restatement of number 2 with logarithms. What do these look like? Well, 10x to the 4 would be very difficult to solve, right? The 10 squared is 100. So to figure out how to get from 10 to 4 with an exponent would be really difficult. But if the variable is an exponent, and only if the variable is an exponent, you can take the log of both sides. That's keeping the equation balanced. Why do I want to take the log of both sides? Because with my log property, an exponent goes to the front. Now that my exponent is now just a variable in the equation, I can solve that. I can divide both sides by log 10 and then type that in my calculator to get my answer. So when the variable is in the exponent, you're going to take the log of both sides. So here, I have the variable as my exponent. Because this is an e, I would take the natural log of both sides. That would be my inclination, because it's base e. I bring the exponent to the front. I divide both sides by natural log e, which natural log e when typing in a calculator is just 1. And then I'm going to divide by 0.02, which is 262.875. In the lab, be really cognizant of where they want you to round to. You want to make sure that you are rounding appropriately. So make sure you're carefully reading those questions to see that final answer and what they're looking for there. Again, I have a variable that is an exponent, so I'm going to take the log of both sides. It's not a base e, so it would be more common to take the log of both sides because it's not base e. I bring the exponent to the front. I distribute my log 5 in. I subtract that over, divide, and I type that whole thing in my calculator. And I get 5.635. When you're entering this in your calculator, please make sure you put parentheses around the top. So you need open parentheses log 9 minus 7 log 5, close parentheses, divided by negative log 5. So in this case, we're going to be looking at when the base of the logarithm and the value next to it is the same. So I have log base 5 of this equals 3. The variable is inside the logarithm. When the variable is inside the logarithm, you want to rewrite it as an exponential. So remember, we take the base, and it becomes the base of our exponent, and then they switch sides. Then you solve this like a regular equation to get 41. So when the variable is an exponent, we take the log of both sides. When the variable is inside the log, we rewrite it as an exponential. So the same thing occurs here, that x is inside my logarithm. So I'm going to do 3 to the third equals the inside of my logarithm. I'm going to take the 3 to the third and rewrite it as 27. I'm going to take the 5th root of both sides, and then I'm going to subtract 1. I can check my work there by typing that into my calculator. Now, do you want to round or not? So here's the thing. If the lab tells you to round to 3 decimal places, you would round this to 3 decimal places. However, if there's not a direction, you're going to want to use the exact value. Here, I have a different situation because I have multiple logarithms. I need to condense the left-hand side into one logarithm. My logarithm rules say if I'm adding two logs, I can multiply the inside of them, and then this log has to be equal to this log. So I'm setting the insides equal because they're the same base. And then I'm just going to solve for x. So the trick is combining them and then solving for x. Here I have two logarithms. I have to combine them. Then I'm going to rewrite it as an exponential because the right-hand side isn't another logarithm. I'm going to distribute it, and then I'm going to solve the quadratic. This is in the lab for homework, guys. Take your time, combine into one logarithm, distribute that x through, rewrite the other side once the exponential is calculated out, and then you would factor. And if you're not great at factoring, guys, you could complete the square. That'd be okay here too. Or you could use the quadratic formula. You don't have to factor that last step. Another strategy is to get all my logs on one side. So I can do that by setting them equal to each other, or I can write it in exponential form. Those are two variations of what I just did. So the applications of compound interest. This is all about how much interest will you have if you invest X number of dollars. So we're going to utilize this formula, which we've been familiar with from other math courses and from earlier in this course. But we're going to start asking ourselves, what happens if time is unknown? So if my time is a known value, I can plug straight in and get a calculation out, and it's not too bad. It's just about plugging in the formula. My rate has to be a decimal. My n is the number of times it's compounded per year. If it's compounded quarterly, that's 4 times a year. I'm just plugging straight in my calculator for this one. Now comes the question, if I want it to double, how long does it take? That's a difference because I'm solving for time. So if I want it to double, I would say 2 times my starting investment of P equals P. I'm going to calculate this whole thing out, and I get 2 equals 1.02 times 2t. Where did the p's go? They canceled out. I divided both sides by p. I'm going to take the log of both sides because when the variable is an exponent, we take the log of both sides. So I can bring the exponent to the front, and then I can divide, and I can solve for t. So really, this is just an extension of what we just did. And you're probably going to need to go back and watch this video again because logs are very fast-paced, and I talk quickly, mainly because we have a lot of ground to cover in these slides. So there is opportunity for you to pause, reflect, process information, or rewind and go back and look at what was learned. This is another compound interest formula. How do you know when to use this formula? It's always going to say it's compounded continuously. Okay, so we call this PERT, P-E-R-T. That's kind of lovingly referred to as PERT in our world. So right here we see in the question, it says compounded continuously. So I'm using PERT. I'm going to look at my principal. I invested $2,000 to start off with. I have 5%, which is 0.05 as a decimal, and I'm doing it at 10 years. I'm just typing this into my calculator, guys. That's it. It goes straight on the calculator. My variable was not an exponent. My variable was on the left. Now, if I want to know how long does it take to double, well, that's still PERT because I'm still compounding continuously. And I want to double my $2,000. So that would be $4,000. I would divide both sides by 2,000, and that would give me 2. Then I'm going to take the natural log of both sides. It's the natural log because this is base e. I bring the exponent to the front. Natural log of e is 1. That's where it went. I divide by 0.05, and I get 13.9 years. There is some room for exponential growth and decay with natural logarithms. It's not incredibly common, but we do sometimes utilize it. Notice in the question, it gave me the formula with an e in it. So you're not going to have to recognize when to use a natural log and when not to use one. So if I have an initial sample, so why not? That's going to mean I'm going to replace that with 12. How many grams to the nearest tenth will be present after 35 years. So I'm going to replace t with 35. And then I'm just plugging in my calculator. So be careful of trying to say every time I see a word problem, I'm going to have to take a log. There are several questions in the homework where you're not taking a log, you're just plugging in, and this is one of them. Now if I want to know what is the half-life, that's how long does it take to half itself. So that would be 6. So I get 1/2 or 6 equals 12. Then I'm solving for t, which means I need the natural log of both sides. So my variable comes to the front. The natural log of e is 1, so that's why it goes away. And I get 29 years. So it takes 29 years to decay to exactly half the amount. It's a long time. And that is the end of logarithms.